Hello all, welcome back. Today's talk is about Shakti. Shakti is a processor developed by IIT-Madras. So this is a processor initiative taken to have open source implementation where you can find all the implementation available in GitHub. It's pretty much the entire bit file, the entire the Verilog stack, the design stack, and the SDK. Everything is open source. So you can basically take this and do customized design for your. You can take this and do some customized implementation, and you can customize yourself. So okay, based on application. That was their intention to have something customizable chip which is used for a specific purpose. So they have this something called as C-class and E-class, where E-class deals with 32-bit RISC-V architecture, and C-class deals with 64-bit RISC-V architecture. So why did they choose RISC-V? So if you see the conventional microprocessors or controllers, they are 8086 or it is ARM. ARM is based on RISC architecture. Also, Shakti is based on RISC-V architecture. So differentiation is this is the 5th generation of RISC architecture, completely open source. So let's look what is RISC-V. So RISC-V is was developed by University of California, Berkeley. The concept was that most processor instructions are not utilized by most computers. So most of the instructions which are already there in your hardware were not being used at all. So this were causing their power issues and cost issues. Okay, so you can customize your hardware. So unnecessary decoding logic were being utilized within the design of processors, consuming more power as well. So to shorten the instruction set and to invest more within the register, RISC-V was invented. I mean, it was developed. So there are two purposes. One is power and reduce the instruction set and invest more on the register level. So that required number of peripherals will be implemented. That is the main goal. So RISC-V is nothing but of reduced instruction set with 5th generation, and it's a freely available open source ISA. ISA stands for instruction set architecture. And if you look at the history, it's there from a very long time now, but it came to picture recently, which it has become very famous. It has become very much sound in the startup world. RISC-V architecture and working. RISC-V is shown below. It's highly configurable with single core. So they have basically two architectures, or single or design instruction set ISA. One is RISC-V based 32-bit and RISC-V 64. Okay, compliant software. So this can compliant on two different architectures, either 32-bit or 64-bit. So of course this is from hardware architecture. RISC itself, the idea behind RISC remains same, but here the idea is to reduce more the number of unused instructions. Okay, so if you just pretty much see the if you see the architecture here, it's pretty simple. So the main goal of RISC-V is to have the 6 level pipeline. So you're gonna have a 6 stage pipeline optimized folded. So RISC has this unique design where you will be having 6 instructions in the queue. So if one instruction is doing the write back, one will be doing execution, one will be in the decode optimizing stage, one will be in a pre-decode stage, one will be in the fetch stage, one will be in execution pipeline. So all these are the instructions being followed when RISC-V is being. So this will make your system more optimized. Your CPU cycles are being used properly, and it is more power consumed. Okay, so this is the design. If you see the design of a CPU, it's pretty much simple here. You have this CPU design and digital unit, configurable interface and optional unit. So only the configurable interface is there here, and you have some the CPU's core work will remain same, except that you're gonna have these required peripherals in it. Okay, so from that we can see what are the advantages of RISC-V. It is industry standard instruction set, parameterized with 32-bit and 64-bit. It has precise fast interrupts, custom instructions, allow the additional and priority hardware accelerators, execution of single cycle. So all these are pretty much instructions which will help you to get the best code or best customizable hardware. Here are some of the more applications. You can find it in the RISC-V website. You can also be a part of RISC-V, can be a member of it. I can contribute because it's open source, right? Anybody can contribute to it. So that's the idea behind it. So this Shakti was built in the ideology of open source community. This open source community is something which is growing up. So they also wanted to, you might have seen how open source software is being built. If you take example of Linux, it has gone like anything. So idea behind building Shakti also same. They look for more contributions and stuff like that. So this idea, this video is more about intro part to Shakti and intro part to Rust. So maybe in the coming, we might talk more on Rust, but this video is, we need to know what is Rust, because many people don't know what is Shakti also here. So we are going a little bit detail about Shakti processor, like how do you use it, how do you where do you get it, that level of detail. So if you go to Shakti process website, the intention of this video is not to give explanation about Shakti's documentation. We will be going towards Rust's documentation next, what we have built. For that, you need this prerequisites, or I can tell you the bridge course is required, bridge thing is required before you get into it. So if you go to official website of Shakti, you can just Google a Shakti processor. You can just land up here. You can find this software section where you can have this Shakti SDK and documents and learn with Shakti. Okay, so there are some pretty videos there, and you can find it. SDK is where you can have their own stack implemented for all the peripherals. You can use that. Documentation is where I am more interested in. If you go to documentation, there are some documentation for initial broad bring up. You might need SDK user manual to how to use SDK, and you might use Shakti SOC register manual. So these two things are very important in terms of initial development. And of course, if you are going ahead, you can use these manuals as well. But for our Rust implementation, we are only focused on these two manuals along with the hardware manual. So let's look into the manual one by one. So let's go to the hardware manual first. So I have this hardware manual here, Shakti Development Board Vajra manual. So this is about if you just see if you buy any chip, right? Hardware manual is just like a data sheet of it, and the SDK manual is something like it's like a reference manual where you have information registers and stuff like that. So in development manual, you can go down here and you can see what is Shakti. So they'll tell you what exactly how it started and stuff like that, about introduction. So we are like more focused on EClass and CClass. So what does EClass do? EClass is a 32-bit/64-bit controller capable of supporting all extensions of RISC-V ISA listed table. Okay, so whatever RISC-V is, so I have been supported here. So the main agenda of EClass was to have a competition with Cortex-M controllers. So they are trying to build a controller which are equivalent to Cortex-M, a market which is basically controller market, which are used in IoT applications, smart cars, motor controls, and stuff like that. So what you can deploy, you can also use RTOS on it, or any free RTOS, or any other real-time operating system can be dumped on it, and you can start working on it. This is the use case of it. It's pretty much very lightweight. So you can just see only two UARTs are there, one IC is there. So one I2C is there, sorry, one PWM, 6 PWMs are there. So this is pretty much used wherever you can customize your chip. This is as near to ASIC, where you can have your own specific application for your controller. Okay, this is the idea behind building the various controllers with various different use cases, with different peripherals here. So you don't need to have all the peripherals. Say, for example, I am trying to build something like a washing machine. I don't need to have a CAN in that. So I have to choose a controller which is like very cheap and also have minimum peripherals, so I can save my power and save the energy, save the power and save the money out of it. That is the intention of having an open source architecture set, and that is the intention of Shakti to use RISC-V and build something crazy out of it. So this is about EClass. So they have mainly EClass and CClass. So EClass is about controller focusing on Cortex-M ka equivalent. CClass is something which is focusing on Cortex-A's equivalent. So CClass is a 6-stage 64-bit microcontroller supporting the entire RISC-V ISA. So it is supporting the entire RISC-V ISA. If you see 32-bit or 64, it is capable of supporting all extensions, but CClass is something which is supporting entire RISC-V ka instruction set. Our target is mainly for is on Cortex-A and A55, A35, and A55 is the target market. So you can run Linux on it, free autos on it, and whatever. So all the heavy lifting OS on it, which is capable of, if OS is capable of having this much capacity of memory, then this can be loaded on it. So idea behind it was this. So right now, if you see Shakti's website, so they have some controllers which is taped out, and there are some controller which is still design phase. Example is CClass and EClass, Vajra, Pinaka, and Parashu are the EClass and CClass based controllers, which is design is available in their website. I'm not sure if this taped out, but there's no information about it. But if you see, there are some tape outs of C-class processor, which is called Remo, where you can get the hardware and you can start working on it. But there are some design which is still in the bit file stage. But you can take the bit file and dump on FPGA, and you can convert FPGA to a particular controller, and you can start working on it. So there is something called Remo, and there is also something called there is RISC-V, which is used by which is basically taped out by Intel with 22 nanometer, and this Remo is taped out of 180 nanometer design technology. Okay, so these are the two different controllers or processors they have taped out, which is 64-bit architecture, and it has 5-stage pipeline. And this is pretty much about the hardware what they have. So what we have is, if you go to the manual of this is the user manual. It's like almost like a reference manual for your development. So if you go here, by the way, you'll find all these documents in your document section of your Shakti. You can just go around and look at what to find where and all. So they have this 3 main controller called Pinaka, Parasu, and Vajra. So these are the processors. I don't think it is taped out, but you can definitely find the bit files of these processors in the website. If you go inside their GitHub, you'll definitely find the link of the thing. I think if you go inside this manual, you'll find a link there. If you read properly, you'll find a link for the .mcs file or .bit file, which can be burnt on FPGA, and you can convert that FPGA to a particular microprocessor or microcontroller. Okay, so EClass is 32-bit microprocessor capable of supporting all extensions of RISC-V. So as I told, it was mainly focused for ARM Cortex-M's market and M's core, and they have so these can be something like specific applications like power compute up environments, automotive or IoT applications such as smart cards, motor control, and home automation. So these are the areas. As I told, you can put all autos and free autos on it. So Pinaka is a processor which actually comes in this family of EClass. This A35 stands for 35T transistor wala FPGA. So design when you're trying to build a very big design, you also need a very very good FPGA where it has more transistors in it. So if you have a very small design, you can go for a less transistor based FPGA. This Pinaka is having a very small design, so you can go with A35, RT7 35T transistors, while 35T means around 35,000 transistors, I believe. So, and Parashu is also a E-class, but you need A100 transistors. So it is you need a transistor which is you need a FPGA which is having 100,000 transistors. So if you're trying to burn Pinaka, you just need 35,000 transistors. You can just go with a small FPGA. So they have been using something called as RT7 FPGA for this. You can Google out RT7 FPGA. Is pretty famous FPGA, but isn't. So the whole development board has this directly burn. So I have been working on something called Vajra. So Vajra is a C-class based microcontroller, which is C64, which is 64-bit architecture. So if you see here, there's something called Pinaka, there is something called Parasu, and there's something called Vajra. So Pinaka is E32, which means E stands for E-class and 32 stands for 32-bit instruction. But E also comes with 64-bit instruction. You have to take care of that. But these two are 32-bit. Parashu also is 32-bit, but it's pretty much has more RAM and more ROM. So basically has more ROM and more memory. So you need some bigger FPGA to program this, where you can see this is 128 RAM and this is 4 KB of ROM, but if you see Parasol, it is 4 KB and 256. This is pretty much bigger, so more the memory, you need more transistors. Okay, the C class has Vajra, which is starting itself with like 4 KB RAM and 256 DDR3 RAM, 256 MB of RAM. So definitely you need the little bigger FPGA. So the preferred FPGA is having 100,000 transistors. So RT700T is a transistor what is being FPGA is what is being used for this. RT700T. You can find the transistor the FPGA here. So the detail about the board, what to select is given here. So Pinaka is supported on RTX 7 35T board. So in the RTX 7, the board name is RT7. RTX 7 is a FPGA. So RT7 is FPGA and RT7 is a board name. So Pinaka is supported there, and Parashu is supported in RTX 7 100T board. And Vajra is supported in RTX 7 100T board. So Parashu and Vajra are pretty much supported in a same FPGA. So you can find the FPGA's diagram here. So this is how the FPGA looks like. This is the FPGA where this is not a full diagram design of it. The FPGA chip is there. FPGA pretty much looks like this. So the first step is itself is to make the convert. See, FPGA is something where it's something like you can program it to, you can make it to custom, you can make it to have a customized IC there. The first step is to burn the respective design of these processors into FPGA. So I have made the SDK in Rust for Vajra, Parashu and Pinaka, but I have tested mostly on Vajra's implementation. So first step is to dump the design on FPGA. Look, if you pretty much follow this documentation, you can do that. You can download the Vivado design suite. You can also look around what is Xilinx ADC. There's also a Xilinx ADC implementation, or it's given here. So you can pretty much look around how to set up, how to convert your FPGA to a particular controller. Okay, its documentation is pretty good. You can do it. Today's talk is not about how to set up, because this is taken care by the IIT-Madras itself. So you can go to their thing, and you can do also learn from Shakti, and you can see how to do it. So I will leave it to you that point. Our focus will be on how do you getting started in building a HAL layer for in Rust. Okay, so before that you need to know all these things. That's why I'm like going in detail about it. Like if you have a Windows machine, you have some installation steps, and if you have Linux, you have some installation steps. Along with it, if you go down, you will find the memory mapping section, which is pretty much important when it comes to FPGA thing. Memory map is important, where you map your particular register to a particular variable, right? It is important. So memory map for Pinaka, Parashu and Vajra is given here. You can go and read around it. And then it comes your section where Shakti SDK architecture. So their platform is written in C and C++. So if you want to test your board, you can just look around, you can read around this documentation, you can burn the code, and you can make it work. So this is about it. This is about your documentation, what they have given. But the idea behind this talk is about Rust in Shakti. So Rust and Shakti is our main topic. So before that, we need to look around for documentation. That's why I'm just going through these documentations, so that it'll be easier for you guys to understand like how do you relate this. This is a third manual, which is called register manual for Shakti, which has information about your particular register. Previously we saw memory mapping, so now you need to have a memory mapping with the offset for a register. So if you go to PWM register, here you will have some offsets like offset 0, 1, 2, 3, etc. So you need to have information about it, and also what exactly every bit is doing. So there's like a reference manual. If you go to NXP, you will have something called data sheet, which will have information about pins and more external stuff, more physical stuffs. And if you go to reference manual, is more about your applications and implementations, where you have what is there inside it and how do you map it and all stuff like that. So these are the manuals which is required to start a Rust code. Along with it, if you go to the Rust SDK, you will find something called as Shakti SDK. If you click that, you will go to this page where they have pretty much implementation for C, where you have something called BSPs, where you will have all the board support packages, drivers and stuff like that, which is entirely written in Rust, written in C, sorry. So they're written in C, and you can test it out before doing it. This is one. And you have something called as, if you go inside software section, and there you will find examples. Inside this you have examples of ADC, UART, SPI, PWM, malloc, and pretty much everything here. So all the peripherals examples are here. If you want to test it, you can do it. Okay, so as I told, the scope of this call is to how do you get Rust inside Shakti. Okay, so now we have seen the user manual where we saw the memory map, and we saw the clear differentiation between EClass and CClass. We saw the register manual where it is clear indication of registers and their offsets and their functionality. And we also saw the hardware manual where we saw the tape outs and different controllers and family. Also, if you go down here, you'll also find the setup available here. You'll also find memory mapping here, and you also find one more interesting, which is called memory pin mapping. So how do you map the FPGA pins to your controller pins? So this is a mapping. So your right side is your let me open. The right side is your pin mapping of your FPGA, and left side is the pin mapping of your microprocessor. So since you're burning the controller on the FPGA, so you need to have this mapping also. So these are the three important manuals which you have to look around before starting. So all this will be available in documentation section. You can start around it. Let's go back to this Rust. Okay, so if you go into the Craze.io, right? If you just Google Craze.io, so I have implemented HAL layer for Shakti. So Shakti RISC-V HAL. So if you search this in your Craze.io, you will find the HAL. So I just published it 3 days back. And if you go, this is like a first release. I'll be doing multiple commits. This is like a first release I'll be doing, which I have done. So you will find the repository link here, and you also find the documentation here. If you go to documentation, you will find explanation about a few things. Like example, if you go to UART, you can see what exactly is there in UART block, register block. So how you can use that, and there's a UART in a register structure which we have defined, and the functions in it. Okay, so all these are there. If you want to see the source, you can also see the source code available for it. It's pretty much everything is available online. Okay, so this is about your doc. And if you go to GitHub now, let's go from the Craze.io itself. Like if you go to a GitHub page, repository, if you just go here, you will find this repository here. So we have been committing every single day. So currently we have done only the HAL layer. There's no examples as such. So we have implemented the UART, SPI, PWM, I2C, the entire HAL layer. So like we just saw the UART, right? If we go inside this, so we can see the UART implementations here. So how do you map it? So yeah, this is about your GitHub page. Let's start exploring the design of Shakti as Shakti HAL. So let's start with device.x file. This is how the code starts. So device.x file is where we give our mapping of your RAM. So where does the text start, text init start, where does the .text start, where does .ro start, where does the .ro data start, .sdata, .sbbs, all these are the sections on RAM. So you have to define the area and all stuff like that, like where it is start and all these things, and the size of it, what is the stack size, what is the heap size, so all this is there in your device.x file. And then next is your memory.x file, where you will be having your starting address of your RAM. So this is a memory mapping. So, and you're gonna also include link.x file. So these two will act like a linker for your main source file. When you compile the source file, it'll look for linker, how do you link it and all stuff like that. This is happening here. And build.x file is a file where you call these functions, which will help you in compiling the code. So this will help you in mapping, and actually physical mapping happens from this if you give a proper path. So if you don't give the path here, compiler will not know what exactly you are trying to do. So those things will be taken care in build.x file. .cargo is where you define your target. So since this is a RISC-V target, we're going to be adding the target here, RISC-V 64 iMac unknown ELF. So before adding this, you have to also do rustup target add, this thing. So this will download, which will download your ISA from thing, and it'll be in your system. It's just simple. You just need to go to add like rustup. If I just do rustup show, you can see the target here, RISC-V 64 iMac unknown ELF. So if you do rustup target add, you can add this, since I've already added it and you don't need to add it again. So let's go to the thing now. So once you need to also have instruction set in your machine, and you also mention target. This will only help you build a target, but actual instruction set should be available in your machine. Okay, that will be happen only when you do rustup target. Only then you can actually download it from the website. Next is your source itself. So we have seen multiple files like memory.txt file, device.txt file, build, and .cargo. So all these will help as a linker and for cross compiling and stuff like that. Next is your cargo.toml. In cargo.toml, you actually add dependencies, external dependencies. So we are using crates like RISC-V RT, panic, RISC-V, and doc registers. The most important register here is doc registers, which is like lifesaver in building our entire crate. If this was not there, then we had to maybe custom implement entire register level coding, like as we do in C. So doc registers have made life easy. It has its own implementations. Okay, you can get few fields and it's like a trait, like trait implementation. So let's go into UART and let's check how did we do it. So we have imported doc registers, and we have some interfaces like readable, writable. Okay, so we have used it, and we have also, there's also called macro called register structs. It's a macro where you can put all your offset. Say you go to user manual now, and you register manual. So you can see some offsets here, 0004, 080C. Those things can be mapped here. So those things can be mapped here. So basically you are mapping the registers with the address. Okay, so which offset, what is there, and you also give the offset of your UART in the beginning. So this is how you give the offset of your UART, and then this is how the UART starts, and after that you keep on incrementing 0002, 04. You will find different registers in the UART. Starting address is this is starting address. So in any microprocessor or MCU, everything is memory. At the end of it, it's all memory. So you have to go write there, and you have to go read there. So there are some registers where both writable and readable access is there. You can do read and write. And there are some registers where only write only is there. You can write only. So all these are the access permissions you will be giving it. Some registers you can only do read only, some registers you can do only do write only, which is already defined by the design of it. Okay, so this step is so step one is to give the address of the UART, and you do the offset mapping for the thing. Okay, so you define the offset of it. Next step is inside the register now. So first step was we were at the surface level. We were at the now we were at the border level. So what we did was we have defined the base address, and we define the address of these registers. So there are, like, say example, if you take PWM, right, you have 4 registers here. So first step was to initialize the address. Second step was to give the offset for these registers. That we have done. Next step is to go inside registers now. So we use something called register bit fields. It's a macro. So we go inside and and set the define the register information, what it is holding. Say now we're gonna say the board is inside UBR. UBR is a register. So what does it have inside it? So it has a UBR is a register which can store the baud rate, right? So at the 0th offset, you can store 16 bits of value in it. Okay. Similarly, USR status register. So it is a register of 8 bits long, and what every bit does, you have to give information about it. Okay. So since stock registers crate I'm using, my life has become very easy. So I can just define it in two macros. I can define the entire mapping of my hardware. If that was not there, I have to do the pointer level implementation and lot of work. I need to define so many functions. I'm like a set and get. There are so many functions I need to define. But talk registers is made my life easy. So which has made my lines of code from maybe 1,000 lines of code to like hundreds of lines of code. So once you have defined already the register level, you have to map it. So now you are doing this step is to map the address with register. So once you are done the mapping with address with register block, next step is to give the physical address. So basically you call the register block and you give the physical address and you map it. So this step is where you have an instance of a UART and you have done the mapping and you have done the offsets now. So now you have the complete control over your register now. So now of a UART register. So whatever you write will be reflecting on your output, on your terminal. Okay. So based on your applications, you can go ahead and implement what all functions you want. You want write UART, read UART, write string, read char. So based on your implementations, based on requirements, you can keep and writing your application level logic. So there are some default applications what we have written, like write, char, read and all. So which will be which can be used to this is like a test of basic functionality of UART. Same thing applies for SPI, PWM. If you go into SPI, you can see there are some 500 lines of code written, because SPI is pretty big register, big protocol where you have multiple registers, and there's also external flash here, so which is used by SPI. So overall, this is a repository. Shakti RISC-V HAL is a repository where we give Rust power to boot up the Shakti processor. So it supports CClass as well as EClass. So this creates a hardware abstraction layer for Shakti CClass Parashu Pinaka and EClass Vajra processor. So pretty much all the current bit file based processors available in Shakti, it supports it. So we'll be adding more examples here. This will be a repository where we'll be adding more examples and more functionality for your registers, and this will be like the foundation for your Rust-based implementation for Shakti. So if you go to the website, you will find documentation for C-based. If you go to craze.io, you will find documentation for Rust-based implementation. So that's all about today's talk. So further, maybe in next talks we can see how to boot up, or we can do some more hands-on coding using these registers. Okay, thank you.